Welcome to this video on frame analysis. In this video, we will count the number of unknowns in free body diagrams and count the equilibrium equations that are available to determine the internal forces in a frame. The number of equilibrium equations must be equal to the number of unknowns, the unknowns being the internal forces when we draw the free body diagram of the members of a frame. In another video, I have shown you how to draw the free body diagrams for frames, and you may like to watch this introductory video before you come to the current one. Before we begin, I would like to draw your attention to this textbook with many solved example problems and this software from Actus Potentia, and this software will help you solve engineering statics problems. So let's first start with the equilibrium equations. To enforce the equilibrium equations, we take a free body and choose a reference point on the free body, and on that free body there will be a number of forces and coupled applied, and we will calculate the force coupled system consisting of the coupled C and a resultant coupled C and a resultant force R at the reference point. The resultant coupled C causes rotational acceleration, and the sum of forces causes translational acceleration. At equilibrium, the body does not have rotational or translational acceleration. Therefore, we set C equals 0 and R equals 0. C and R are vectors. In two-dimensional problems, C has only one component and R has two components, whereas in three-dimensional problems, C will have three components and R will also have three components. Equilibrium of a point mass: when the mass does not have any size, and the rotation of a point mass is meaningless. In that situation, the resultant couple is automatically 0. Therefore, for a point mass in two dimension, we have two equilibrium equations, and for a point mass in three dimension, we have three equilibrium equations. For a body of finite size, in in two dimension, we should have Rx equals 0, Ry equals 0, and Cz equals 0. And in three dimension, there are 6 equilibrium equations that each component of the force, Rx, Ry, Rz, they are 0, and each component of the couple, Cx, Cy, Cz, they are 0. So altogether 6 equations. Now let's look at the free body diagrams. So to summarize, for a point mass, 2 equations or 3 equations in 2 and 3 dimensions. And remember that the pins are point masses. And for a body, 2 dimension, 3 equations, and 3 dimensions, 6 equations. The equilibrium equation for a two-force member is simply F equals F, and it's useless because all you get is F equals F, but from this equation you cannot determine the value of F. So we will draw the free body diagram of the two force members, but they will not be included in the solution process. So this is our example 1. We have two members and a complex pin, so we can draw 3 free body diagrams. And we have drawn these free body diagrams in another video. If you are unfamiliar with complex pins, then you should watch that video before you come here. So let's draw the free body diagrams. So now the free body diagrams are drawn, and so you can see some action-reaction pairs here, BX, BY, and action-reaction pair, F and F. So altogether, I can see that I have 5 unknowns, AX, AY, BX, BY, and F. And we have 5 equations. We can write 3 equations for body 1 because it's a finite sized body. For sum of forces in the X is 0, sum of forces in the Y is 0, and the moment at the reference point is 0. So 3 equations for body 1 and 2 equations for the pin because pin is a point mass. So we have 5 equations and 5 unknowns. We can solve this problem. And this solution part will be handled in another video in the future. Second example, the free body diagrams, pin support, the bottom 2 force member, vertical 2 force member, inclined 2 force member, the connection at the middle pin, the forces at the middle pin on the top bar, and the right pin. Count the unknowns. Altogether we have 9 unknowns, AX, AY, BX, BY, CX, CY, F1, F2, F3. We can write 3 equations for body 1, 2 equations for pin 1, 2 equations for pin 2, and 2 equations for pin 3. So we have 9 equations and 9 unknowns. We can solve this problem. Example 3, we have one body. We have one body here. This is a 2 force member. Second body. So we have 1, 2 bodies, and a complex spin equilibrium equation, free body diagram, and a complex spin equilibrium equation and free body diagram. Let's draw the free body diagrams. The L-shaped body has a roller connected in the middle with a complex pin, connected at the top with another complex pin. The second member on the right connected to the complex pin, 2 force member, and a support pin at the bottom. Altogether 10 unknowns, AY, BX, BY, CX, CY, DX, DY, EX, EY, and F. We can write 3 equations of equilibrium for body 1, 3 equations for body 2, excuse me, 2 equations for pin 1 and 2 equations for pin 2. Example 4, we have 1 multi-force member, 2 multi-force member, 3 2 force members, and 2 complex pins. Draw the free body diagrams. Complex pin 1, which is here. Two 2 force members meet there. These two red arrows are the support forces coming from this pin. This red arrow is coming from the roller. Green arrows are the loads. You have two of them. And all the blue arrows are internal forces or action-reaction pair of Newton's third law that we exposed by separating the bodies. In this problem, there are 12 unknowns and 12 equations. 3 equations for body 1, 3 equations for body 2, and 2 equations each for pin 1, 2, and 3. So 12 unknowns and 12 equations. Next example, we have a 2-force member, a 2-force member, and a 2-force member, a multi-force member, a complex pin here, here, and here. This pin is complex because 2 members and a force interact here. And a pin is complex when we have more than 2 interactions. 2 members and a force, 3 interactions. 2 members and the wall, complex pin because 3 interactions. Drawing the free body diagram now. This is the force from the top pin here. This is pin 1. Bx, By are the reaction forces from the wall, including the 2-force member, the inclined one, the bottom horizontal one, the right vertical one, and the complex pin at top right. Again, as before, the red forces are from the wall, greens are the loading that we applied, and the blue forces are the forces that we are interested in. And how many do we have? 9 of them. We can write 9 equations, 3 for body 1 and 6 for 3 pins. A multi-force member here, this is multi-force because a couple is acting on it. 2-force member, 2-force member, 2-force member, and a complex pin. This pin is complex because we have 3 interactions, pin, pin, piston. Drawing the free body diagrams. That is the force from the wall at the top pin. The first inclined 2-force member, the second 2-force member, this is the complex pin where we have 2 2-force member and the piston. So CXCY is the interaction between the complex pin and the piston. Now, support force from this pin, and these two are the reaction forces. Dy is the reaction force coming from the blue casing of the piston, and dx is coming from this green substance that the piston is squeezing on the right. 10 unknowns and 10 equations. 3 equations for body 1, 3 equations for body 2, and 2 equations for pin 1, and 2 equations for the point mass. We consider the piston as a point mass because its size is not given, and whenever a size of an object is not given, you must consider that as a point mass. A pulley problem, drawing the free body diagrams. The green arrows are the tensions in the cable. At this pin, which is this pin, there are two tensions along these two segments of the cable. At this pin, which is this pin, there are two tensions coming from these two segments of the cable, and this segment of the cable applies a tension at the complex pin here. Although this member is not straight, but still it's a two-force member, so the two forces will be aligned with this line joining the 2 points of applications. Complete the free body diagram. The support pin on the left, and this is the interaction between the support pin and the bottom horizontal member. Two-force member, interaction between the vertical multi-force member and the horizontal multi-force member at this pin. Now we have to add the roller. That's the roller force. There are 8 unknowns: AX, AY, BX, BY, CX, CY, DY, and F. And there are 8 equations. 2 equations for body 1, 2 equations for body 2, and 2 equations for pin 1. Whenever you are doing a frame analysis, first, of course, you isolate the members and isolate the complex pins and draw their free body diagrams. And you must do this counting before you get into the solution. If you are getting number of equations to be equal to the number of unknowns, only then you know that your free body diagram is correct, and then you can do into number crunching. Otherwise, if you jump into the math without the counting, you will have a lot of wasted effort. Next problem. 2 tensions at this pin from these 2 segments of the cable, and 2 tensions at the right pin from 2 segments of the cable. Here we have 2 multi-force members, the top one and the L-shaped one. The L-shaped one has a tension on it from this cable. So these tensions get exposed when you cut the cable here and here. To expose the tensions in the cable, you have to cut them here and here and separate them into segments. Let's draw the free body diagrams. Top support, bottom support, the junction between 2 multi-force members, and Newton's third law. 6 unknowns, 6 equations, 3 equations for body 1, 3 equations for body 2.